All right, let's get started. So my name is Hotaka Maeda. I work for Smarter Balanced. I'm a psychometrician, and this is the first time attending this conference, and I'm finding out that my presentation's quite different from everyone else's. It's a lot more technical, a lot of numbers, graphs, but I'll try to break it down for you because I know most of you are not psychometricians. So I'll be talking about field testing using artificial intelligence. So I'll start with some background on AI. I'll be using the term AI often in this presentation, but what I really mean is natural language processing. So NLP is just one branch within the field of AI. And NLP is concerned with providing computers an understanding of text and language. A couple of years ago, I found out that Google invented something called the transformer. And these transformers, they provide a foundation of almost all AI we see today, including ChatGPT. Compared to the predecessors, transformers are very fast. And this is important because the faster the model, the more intelligent we can make it, more complex we can make it, and then it will still run pretty quickly. Transformers are able to understand the context of words. Like the difference between phrases write a check and check the engine. The word check is being used in a different meaning, different context, but transformers are able to understand that. And when we first use transformers, we have to teach it a language like English. If we want to teach it English, we have to feed it a lot of English text. The second step could be to fine-tune the model to a specific task, like question answering or language translation. And this is not important to understand, but it's kind of interesting to see. So the core of transformers is what's called a self-attention mechanism. And self-attention is like correlations between the words. So you see here on the diagram, a transformer is processing a sentence. And you see the same sentence at the top and bottom. And the transformer is making connections between the words. And those are the attention weights. And so somehow transformers are able to understand the meaning of the word just by trying to understand its connection to the other words in the sentence. I think this kind of makes sense intuitively if you think about when we look up a word in the dictionary, what do we see? We just see a whole bunch of other words associated with that word. So I think that's kind of similar to what's going on here. There's lots of ways to categorize AI, but I want to talk about discriminative and generative AI. So generative AI is AI that's capable of producing new content, like new images, new text, new sounds, audio. In the assessment industry, we can use generative AI to write new items, automatically generate items. And ChatGPT is a generative AI too. Discriminative AI is capable of looking at an observation and categorizing it. Like, for example, identifying a car from an image would be discriminative AI. In the assessment industry, we can use discriminative AI to score essays. So what happens is the transformer would take in the text of the essay and try to categorize it into a certain score, like 0, 1, or 2, and so on. And in my view, automatic item generation and automatic essay scoring are the two areas in assessment where AI has been applied the most and researched the most. So when people talk about AI in assessment, oftentimes they're talking about item generation and scoring. So you may have noticed that field testing is not on this list. This presentation is about field testing, so and this means not a lot of people are trying to apply AI for field testing. So let's talk about field testing. Field testing is a process of trying to gather data for newly written items to try to calculate various statistics and evaluate the quality of the items, and also to calibrate the items for scoring. At Smarter Balanced, we have somewhere around, what we do is we have somewhere around 25 to 40 operational items that are scored, and a few field test items that are not scored. And students would get operational items and field test items and take the exam without knowing which type of item they're taking. And at the end of the year, the psychometricians would look at the data and do field test analysis. And that's cool, but there's a problem with this approach. And it becomes apparent when we look at the timeline. So this is an example timeline at Smarter Balanced, field testing timeline. So let's say we finished writing the item in fall of 2022. We have a process of trying to package those items into a test and then send it off to our vendors. Our vendors are the people who actually administer the exams to our students. And then the students will take the exam for a whole year. And we have another process at the end of the year of gathering the data back from the vendors to us at Smarter Balanced. And that takes a few months. And then the psychometricians would do field test analysis, calibration. The final step is data review. And what we do there is look at the results from field testing and categorize whether these items are ready for operational use next year or they have to be rejected. So this whole field testing process takes 3 years to complete. And it doesn't matter if we're field testing one item or 10,000 items, it's gonna take 3 years. Especially when states demand us to, if states are interested in changing their blueprint or creating a new exam, we're not going to be able to meet those demands for at least 3 years. And this is excluding the time we need to write items, right? And especially if we're able to, in the future, generate items very quickly using AI. If we're able to field test them very quickly as well, there's a lot of potential, right? We could be writing so many items, creating so many items, and adding so much to the item bank. We could write items specifically for minority groups or specifically for California, so on. So, past couple of years, I've been thinking this question. Can we use AI to make field testing more efficient? So let's look at, So let's look at the background information, background research, what other people have done in this area. There's actually a lot of people using models, in AI and non-AI models, to try to predict difficulty of items using item features as predictors. For example, for a reading comprehension item, maybe the number of words in the passage is related to the difficulty of that item. Because more words there are, maybe it's harder for students to understand. Or maybe short answer questions are harder than multiple choice questions. Or maybe there's certain areas in the blueprint that are harder than others. So researchers would use those features as predictors to predict the difficulty of the item. Sometimes it's successful and sometimes it's not. It kind of depends on the type of item, type of test. So there's inconsistent results. But one company took this idea to the extreme and they were pretty successful at it. And it's Duolingo. So Duolingo, they created this specific item type. It's kind of blurred. But so what students have to do is they read the sentence and there's blanks that they have to fill. Using the words around those blanks as hints. Duolingo created this item type specifically because this is exactly how AI processes text. So if you remember when I talked about self-attention, to try to get an understanding of a word, AI would look at its connection to the other words in the sentence or the paragraph. So Duolingo's they've been using this item type in their English exam and almost bypassing field testing completely. So that's pretty impressive. There's a few problems though. At Smarter Balanced and also lots of other organizations, when we do field testing, we not only look at item difficulty, we look at a lot of other things, like item discrimination, distractor analysis, which is the incorrect options in multiple choice questions. We look at bias using differential item functioning analysis. And also just having data, raw response data from field testing is really valuable because we can do any analysis if we have the data. We're not limited to just item difficulty. So I have an idea, sort of a futuristic idea that we're not going to solve today, but it's kind of like a goal that I'm trying to head towards. So my line of research is heading towards this direction. So imagine that we have a diverse range of AI bots. Okay, it's not just one AI model. It's a whole diverse range, multiple AI models. And they're all different. Some are low performers, so they would score low on exams. Some are high performers. They would score high on exams. We could even incorporate people's background information like gender, race, cultural backgrounds, even personality. The whole point is to try to capture the diversity of humans with AI. And then what we could do is get those robots to answer questions. Answer every single item we have in our item bank, including field test items. And then we could do field test analysis using those data. So like if you hear on the news like AI might replace our jobs, this is basically AI replacing our students. Except it's in a good way because to the students, they just get a shorter exam. They don't have to take field test items anymore. And these images were generated with generative AI. So I was wondering whether ChatGPT is capable of doing something like this. Like, if I ask ChatGPT to become a certain person and answer a question as if it was that person. So what I did was to ask it to be me, my second grader self. So what I said was, pretend you are Japanese and born in Japan. You're currently 7 years old and immigrated to the United States last month. You live near Seattle, Washington. Your English literacy and writing skills is 2 standard deviations below the average compared to all second graders in Washington State. What is the definition of psychometrics? So, I've met enough people to know that most people don't know the definition of psychometrics, even adults, especially 7-year-olds, especially someone who's just immigrated from Japan and they barely know any English. And this is a true story about me. I don't know about 2 standard deviations, but it's roughly. So what did they say? The response, psychometrics is a big word that means science of measuring, studying things like how smart people are, how they learn, how they do on tests. So it was able to answer the question. Not the answer I was looking for. Maybe I should have tried GPT 4.0. Would have been smarter, but no. For now, it didn't work. So this is one of the problems that I see is most people working on AI are trying to create AI that is as smart as possible. But I'm more interested in creating AI that's represent real humans. And people make mistakes. People get wrong answers on questions. So how do we create AI models with various levels of performance? Some low performer, some high performer. So my idea is to use psychometric models. Because psychometric models are specifically designed to capture human performance. That's why we use it for scoring exams. So my research purpose is to explore the feasibility of AI field testing by creating large language models that have various levels of performance. And we do this by training the AI using simulated data from psychometric models. So we use psychometric models to create the training data. So the AI would be learning from the psychometric models. You can think of it as I'm trying to create psychometrically human-like AI models. So how did I do this? Methods. More robots. At Smarter Balanced, we have a really big item bank, tens of thousands of items. And for this study, I wanted to just focus in on one area so the data are more manageable. And also if the items are similar to each other, I thought that maybe the AI would have an easier time learning how to answer those questions. So what I did was to take 512 items from our massive item bank, and these are all English grammar questions. And they're also all 4-option multiple choice questions. And then they're designed for grades 3 to 11. And the nice thing about these items is that they've all been field tested before. So I have item statistics on these items. So what I can do is field test them using AI and compare the results between AI field testing and human field testing. So the procedures is this. It's kind of complicating, so I'll take you through it. We start at the top here. So I had 512 items, and the first thing I did was to split those items into two categories. One is a much bigger category of, I'm calling them training items. 417 training items. In a real exam, these would also be scored operational items. And these are items we use to train the AI. The other group of items are the field test items, and I also use these items for evaluating the study. And then what I did was to generate 1,000 numbers, just random numbers that represent the AI's intelligence level. And since we're talking about English grammar items, these numbers represent English grammar skills. So low number represents low English grammar skills, and high numbers represent high English grammar skills. And using these numbers, the English skill levels, and the training items and their statistics, I'm able to generate simulated item responses on these items. And simulated responses are just whether you got this item correct or not. It's just zeros and ones. 0 is incorrect, 1 is correct. For every single item, for every single AI. And I use that to train 1,000 different language models. And the next step is to get all those 1,000 AI models to answer every single item in the study, all 512, including the field test items. And then we do calibration analysis and compare the statistics between AI field testing and human field testing. And hopefully they're similar. So I know this is a lot, so what I'm going to do is to try a little AI demo. Hopefully this works, because I need internet to work. So this demo I'll take you through this yellow box, and instead of, I don't have time to train 1,000 models, so what I'm going to do is get you all to answer a little quiz, an online quiz. And then it's only 6 questions, and they're questions from the study. So 6 out of the 512 items. So they're English grammar questions. And then what I'm going to do is take your data, take your responses, and combine everyone's responses into one bin and score it. So I'll give you one score that represents your English grammar skills of the entire audience. Okay? And then I'll use that score to generate responses, and then use that to train one AI model that represents, that has the English grammar skill levels as all of you. So if you do really well on this quiz, you're going to train a really smart AI. If you do really poorly, then you're going to train a poor performing AI. And I was thinking about this. Maybe it's okay if you intentionally get wrong answers on the quiz. That I think that'll be fine too, because seeing results from a mediocre or poor performing AI would also be interesting. So it's really up to you how you want to answer the questions. But this is the QR code. If you don't want to use the QR code, you can go to this web link. You can come up front if it's too small. So I'll give you maybe 5 minutes to complete it. Again, it's just 6 questions and multiple choice. It should be easy. Any questions at this point? going to start downloading the data. All right, so I got the data. I have the data, and I'm going to run this code to score these quizzes and produce a report. And now I need to use that to train the AI. This is Python. All right, so while that's running, we can look at the results. Okay, so this is a summary of the results. We had 23 people complete the survey or the quiz. And so the first column shows the item numbers 1, 2, 3, 4, 5, 6. The second column shows the correct answers. And third column shows the percent of you that got these items correct. 30%, 83%, 65, 39, 57, 70. And then in the total is 57%. So overall score is 57% in terms of the percentage. And the last column shows the text associated with the correct option. And then what we could do is score it to a scaled score instead of a percentage. But before we score it, we can take a look at the scores from our students. So this is our students, grades 3 to 11. On the x-axis, we see the English literacy scale scores. These are histograms, so the density or the height represents how many students are in those score categories. So as students move up levels, we tend to shift to the right, meaning they tend to get a higher grade, higher score. If we plot your score here, so that's your score. It's kind of small. It's 2,620. So to interpret this, you could say that you're scoring above average for 11th graders. All right, so and we could, there's actually a lot of things I could do with this number, 2,620, using psychometrics. And I'll show you. It's kind of small, but this is what's called an item response function for the first item in the quiz. And this is called a two-parameter logistic model. It's a psychometric model. On the x-axis, again, we see the English literacy scale score. And on the y-axis, we see the probability of getting this item correct. So the higher your scaled score, the higher chance that you'll get this item correct. Makes sense. And students with very low ELA scores will get the item correct almost 0% of the time. And students with very high performance of ELA scores will get this item correct almost 100% of the time. To make this graph relevant to you, we could plot your score on here. It's also kind of small. Again, 2,620, and where it crosses is 0.467. So that means you have a 46% chance of getting this item correct based on your English grammar skills, based on the quiz. And this probability is really powerful because I can calculate this probability for any of the items that you've never even seen before. So we have thousands of items in our bank, in our English literacy exam bank. And I can calculate this probability for all those items. So for example, I plotted 20 different item response functions, 20 items that you've never seen before. But because I have your score, I can predict the chances that you'll get these items correct. So for example, so this is your score. The easiest item for you will be at the top, will be crossing at the top. So you have about 80% chance of getting this item correct. The hardest item is at the bottom. You only have about 20% chance of getting this item correct. And because I have these probabilities, what I can do is generate simulated responses as if you took the item, as if you took the exam. So if you have an 80% chance of getting the item correct, then 80% chance that I generate a 1 instead of a 0. A 1 represents correct, 0 represents incorrect. Usually in psychometrics, zeros and ones are all we care about. All right, so I think the training is done. Yeah, so the AI is trained. Okay. let's look at the results. Hold on a second. Okay, so what we just did was to fine-tune a language model called DBERTA v3 large. That's just the name of it. And we fine-tuned it for a binary classification model because it's capable of taking in text and categorizing it into correct or incorrect English grammar. That's all it can do. So 2 categories. And again, we used your score of 2,620 to train this model. So let's look at the training data first. Okay, so this is the training data for one of the items on the quiz. It's kind of small. So the first column shows A, B, C, D, and D is the correct answer, so it's highlighted. And the middle column shows the text associated with each option. And on the third column, we have a label. These labels are zeros or ones. And this is generated from the psychometric model. And the label is what we're teaching the model, the AI model. And I'm repeating the responses 4 times. So you see 4 A's, 4 B's, 4 C's, 4 D's, because psychometric models are probabilistic models that don't always give you correct or incorrect. It's based on probability. So by generating 4 different responses, I'm sort of augmenting the data. I'm giving more training data to the AI. So what's interesting here is this is the correct answer. So if we're teaching the AI the correct answer 4 different times, then these labels should be ones 4 times. But what we see is one of the 4 times we're teaching it the wrong answer. Right? So we're teaching the model to sometimes get this item incorrect. In other words, we're not trying to build the smartest AI. We're trying to build an AI that matches the performance level as specified by the psychometric model. So after the training, we get these probabilities, the P's, at the very end, for each response option. And these P's, this is the same item number 2. These P's represent the AI's confidence level that this text has correct English grammar. So if it's able to do English grammar, then the percentages should be low for the incorrect options, and it should be high for the correct options. And it is. We see 4%, 4%, 3% for the incorrect options, and 90% for the correct option. So it's capable of identifying correct English grammar. Not perfectly, because these are not 0% and 100%, but it's pretty good. And so I did this for all the training items. And so now we have a model that is capable of distinguishing English grammar. Yeah.
Why does it add up to over 100%?
Yeah, good question. It's because I used binary classification model 4 times. So what I did in the study was to add these percentages up and divide it by that percentage, so it adds up to 1. So I'm not showing that step here. So at this point, what we could do is give the model some new sentences that it has never seen before, and try to see if it's able to catch correct and incorrect English grammar. So I wrote some new sentences. And they're about me. I work for Smarter Balance. And the second sentence, this Smarter Balance is lowercase, it's not capitalized. And the model is able to catch that the first sentence has correct English grammar, or it's pretty confident, 89%. And then the second sentence gets 6%. So it's saying that it has wrong English grammar. So that's impressive because the model is able to identify that Smarter Balanced is a name and it should be capitalized.
Well, how does it know? I mean,
Just like how we know.
I mean, did you give it some parameters to, because a Smarter Balance could also be a regular text, right?
Right. So usually the words smarter and balanced are lowercase,
Yeah.
but the transformers look at the context. So it says I work for in the beginning.
Oh, so by looking at the work could be the keyword.
Yeah,
Associate that means you work for a company, so
Mm.
I have to make it up.
yeah. Yeah.
So, how many training records were necessary to achieve this result? Or are you leveraging the transformers principally and not training data that you've otherwise created?
What's important is the number of items I use. So I use 417 items. So the more items we have, the better. Yeah.
Thank you.
Hmm?
I guess maybe I don't know if this is the same question, but are you taking a AI model that's already been trained and then
Right.
modulating it with additional data?
Right.
Rather than
So
you're not training it from the ground up. You're taking one that's already been trained and using additional data to augment its
Right.
functionality, right?
yeah, so it already knows English, and then I'm training it to identify English grammar. It's called a fine-tuning process, which is the second step of using transformers.
But do you know what the percentages would have been for those two sentences if you hadn't done the fine tuning?
It's just not able to calculate these percentages. Yeah.
I guess, Mike, are you training it to recognize perfect grammar, or are you now training it to act like a student, so to speak, with a particular skill set? Like, are you
Yeah,
saying?
the second.
Yeah, so you've already trained your AI to be
Mhm.
perfect, but now you're saying, now act like someone who got this score.
Right.
Maybe.
An above average 11th grader.
Slightly.
yeah.
So if you make it an English learner,
Mhm.
like a foreign or a migrant, do you think AI would discriminate based on that, or would it just ignore that and follow that?
Yeah, we could potentially create a model for English learners and try to create AI that represents English learners. Yeah.
Because the concept of understanding would be different from a person who's a non-native
Mhm.
versus who's a native speaker.
Mm. So another sentence. This is also about me. I played American football and practiced karate in high school, and now I play rugby on Saturdays. The second sentence has football misspelled. And it's able to, so the first sentence has correct English grammar, and the model says 88%. The second one is 4%, because football is misspelled. Another sentence. I like spending time maintaining and modifying my car. And the second sentence says, I like spending time maintaining and modifying my car. There's an extra A. So again, the model is able to detect that. 90% and 3%. And last one, something I wanted to try. These two sentences both have correct English grammar. It says, I'm from Seattle. I'm from Moroyama. Moroyama is where I was born. So it's a place in Japan. And the model says 91% for Seattle and 83% for Moroyama. So this is AI bias. Probably somewhere in the data, in the training data, Seattle or a word similar to Seattle was in there. So the model is, and the word Moroyama is maybe more rare. So the model is more confident that Seattle is correctly spelled versus Moroyama. To be fair, Moroyama is a much smaller city and it's from a non-English speaking country, so but it is biased and I don't have an answer, but it's good to think about.
So how do you unbias it? That's the challenge, because
Mm-hmm.
you hear all this stuff in the news that, I think it was one with Amazon, they were using an application, using AI, and then they were excluding females or something like that. So there were certain keywords it was looking at, and they were just kind of like segregating the biasing the. I know it's kind of hard.
Yeah, it's hard.
Unless you give it all the countries, cities.
Right. Yeah, it's hard, but I think if we try to specifically address bias, maybe there's ways to build AI that detects bias. So maybe we'll be able to detect more bias than we do without AI. Okay, so that's the last sentence. So let's go back to the PowerPoint. All right, so again, this is what I went through, the yellow box, and unlike the demo, in the study I generated or trained 1,000 different models. So let's look at the results. Yeah.
So from our demo, average use for about 56 drugs. So does that mean when we run through the AI model that we would expect somewhere around the capture rate is about 50 to 60 as well, or is that going to be higher?
50 to 60.
So for our sample, that how we respond to the survey before,
Mm-hmm.
the average, I think of this was like 56%
Mm-hmm.
average. And when you run through the model, it's for, I noticed that it's for significantly higher.
Oh, it should be about the same. it's not going to be exactly the same, but since your score was about 57%, the model we trained should be performing at around that level.
If it was asked the same question.
Yeah, right.
So, but with
Yeah.
those examples, they were much easier type of examples, so above average 11th grader should be able to get it at a higher rate
Mm.
with the more basic sentences.
Right.
So it really depends on how the question is being asked.
Yeah.
Instead of how the result, we actually generate it. It would seem to be if you put in a question that is much more complicated than what was asked on the survey, then that would be I would say, give us a better forecast to see how a typical student would respond to a question that may haven't been harder than what makes those people.
Right. Yeah, the difficulty of the items are taken into consideration because this is based on psychometrics. And I guess for items that are, they ask questions in a tricky way, it's also, we may need more data, more items to train the AI to get it to learn how to answer those questions. So, all right, so results. So what do we look for in the results? The important thing about field testing is that when we score students using the items we field tested, regardless of whether we use AI field testing or human field testing, we should be scoring the same way. We should be providing about the same scores. So that's one thing we could compare. And in psychometrics, there's something called a true score and an estimated score. The true score is your true ability levels. And we use exams to try to measure the true score, but exams are never perfect. There's always some level of measurement error. So there's always some difference between the true and estimated score. So this difference represents the accuracy of the scores that we provide to the students. So this difference is what we can compare between AI field testing and human field testing. So let's look at human field testing first. Okay, this is kind of hard to see. So what I did was I had, again, 95 field test items, and I pretended that these 95 items make up an exam. So, and I had 1,000 simulated students and simulated, just sort of pretended that they took an exam of these 95 items, and then I scored them based on these items. On the x-axis, we see the scale scores again, the true scale score. The y-axis is the estimated scale score. If these students get an identical score, if the true and estimated scores are identical, then these dots that are barely visible they should be following this black line. And to some extent, for the most part, they are. Students that have a high true score will also tend to get a high estimated score. And that's represented by the high correlation of 0.98. But the estimation is not perfect. There's some variation away from the true score. And that's represented by RMSE, root mean squared error, which is the standard deviation of the difference between true and estimated score. And if there was bias, then there would be separation between the red and black lines, but there's barely any bias. So again, this is human field testing, and this is what we want to see in AI field testing, because we want to be reporting similar scores. So let's look at AI field testing. The correlation, which is the general trend, the upward trend, and the RMSE, which is the spread, the vertical spread, are similar to human field testing. But the problem is that there's this little bias. So what this means is, so since the red line is below the black line, what it means is if students take our exams and take items that are field tested using AI, we would be reporting scores that are lower than what they deserve. So the scores will be too low. And so that's not good. The good news is everything else looks fine overall. The correlation, RMSE, pretty good. So if we can figure out this bias, figure out why it happened and try to fix it, maybe AI field testing becomes more viable. So let's look at this bias. So I had 95 field test items, and for some items, AI field testing worked really well. And for some items, didn't work so well. What I did was to take the item in the middle, and this is that one item. So it represents the average results. X-axis is showing the true scores. Y-axis is showing the probability that the student will get this item correct. So again, it's an item response function. Red is AI, blue is humans, or human field testing. What we want to see is the red line and blue line overlapping completely, which is happening over here, up here, but at the lower end, there is a separation. So what's going on is, if you think about the items that we're using, they are 4-option multiple choice questions. So if you think about a student that knows no English, they can just guess on the item and get it correct 25% of the time. And the AI model is capturing that guessing rate to an extent. You see all these dots just lingering at 25%. But the results from the human field testing, the 2-parameter logistic model, is not designed to capture guessing rates. So that's the difference. AI is capturing guessing, and human field testing,
Did you use 2PL or 3PL?
2PL.
Guessing is the 3PL model.
Right, yeah.
So, okay. So I see the CERA and the differentiation is different.
Mm.
Like A and B. So like human is more differentiating. So AI is less differentiating. And the CERA, the true ability, same as the human, is higher than the AI. So what's the reason behind it? So from this chart, we can see the true ability for human is higher than AI, and also the differentiating the B, the human like is more differentiating than the AI. So why is the difference?
So for the AI model, even if you get the item correct, the model says maybe you just guessed. So you don't deserve a very high score. Right? So your estimated score becomes a little lower. And yet, as a result, this slope is less steep for AI compared to the human. And this difference of the slope is what I saw when I compared the individual item parameters between human and AI field testing. Lots of numbers, but you just look at this. There's a less steep of a slope for AI models.
What's the tolerance range for your bias? Do you have like a range or cutoff?
That's a good question. I don't. Yeah, but at this point,
Pretty good. Every point online is small.
well, no, it's pretty big considering the average is like 3.3. So
Oh, the average.
yeah. If we fix this bias, as a result of that, all the other numbers will improve too. So, yeah. All right. So discussions. More robots. So in general, we were able to field test English grammar items using AI by creating lots of language models that have varying levels of performance using training data generated from psychometric models. The problem was that AI captured this guessing rate while 2PL did not. And I think one of the keys to the next step is to try to figure out this bias, try to fix it. There's several things we could do. We could use a different AI model. We could use something not 2PL model, like 3PL. The problem is Smarter Balance does not use 3PL. So, and there's problems with 3PL as well. There's unique problems. We could also avoid using simulated data from psychometric models. So use raw human student response data just directly and use that as training data. Come in.
Sorry.
And also in the future, I want to see if this AI field tested data can be used for supplemental analyses like differential item functioning to identify bias. We also want to expand beyond just grammar items or multiple choice questions. So to sum up, I'll just go over some pros and cons of potentially transitioning into AI field testing. I'll start with cons. AI will never behave exactly like humans. So there's some level of extrapolation or prediction involved. We must address AI bias and ethics. It's going to take time and money. And we might need to generate a lot of data, potentially writing new items like Duolingo did. But there's also a lot of pros. The big one is we could shorten the 3-year field testing cycle by multiple years, maybe down to a few months, maybe even instantaneous. It's probably going to be cost effective because increasing the number of models is probably easier than increasing the number of human students. There's lots of reasons why AI field tested data could be higher quality than human field tested data. For example, AI could take every single item in our item bank, while human students can only take like 30 to 40 items. That's going to give us much higher quality data. And also, AI is not affected by, what's the time here?
43.
Oh, 43, okay. Not affected by problems that lower human data quality. For example, cheating or students not motivated, testing environments distracting, AI is not affected by those things. We can also field test without exposure, and that's nice for several reasons. Students would see a shorter exam, but also we're taking away items that are potentially poor quality. These items are newly written, so they haven't been tested for bias, item quality. They could be confusing, too easy, too hard. By removing those items from the exam, we're pretty much improving the quality of our exams. Yeah.
Does AI look at the distractor responses or is it only?
Yeah, it does.
So it can, you can discriminate between like very enticing
Mm.
distractors versus
Right.
all that goes in there, not just get it right.
Yeah.
And, sorry, I have another question.
Yeah.
So, I think, yeah, so it can shorten the years, the time, but, what do you think, if this will work in the future, how often do you think you will update the items bank? Because students' population will change, how often you will change your parameters, and what parameters do you use to train the AI? So, two questions.
So in the ideal world, we could automatically generate items designed for each specific student and automatically field tested using AI on the fly. And basically design an exam just specifically designed for every single student. That could
So
be
you think
possible.
the student's ability won't change, the theta won't change
Mm,
over the years?
well, we could still try to calibrate it to the same scale. Yeah, we probably don't want to forget the foundation of psychometrics and being able to interpret the scale scores. But I think being able to generate items and field test them quickly would make exams much more flexible. I'm out of time, so thank you for listening. If you have more questions, please ask me. I have business cards up here. Please take one. I'll be here for a while.